I think he sent an email about it. I'm just opening it. Let's see.
Hey everybody, welcome. I just picked up on some chatter. Does somebody have a question?
Yeah, I was just wondering if we turn in the molecular line drawings section underneath where
Yes.
we have chem activity 1C, 1, 2, and 3. We turn that
Yes.
in with 1, 2, and 3?
Yes, that's all one thing. Yep.
Great, thanks.
Okay, let's get started. So welcome to lab. And just to remind you that these were things that were due today. There's the lab report for the copper cycle lab. And then there was that pre-lab assignment, just page 72, which was you doing the flow chart. So let's see, last week's lab. Now, just to answer a couple of questions, I'm able to get in there and grade on your lab report directly. Well, not directly, but on electronic version with my electronic pen. And you will be able to see those feedback files for things that I grade if you go to D2L and then go to where it says assignments. So go back to that assignment where you uploaded it, and you should see a feedback file. So instead of writing the feedback in the little feedback box that's there, since I'm able to write directly onto your electronic version of your lab, I can write on there and give you more meaningful feedback. So I just want to let you know, when you see that feedback, first, I apologize for my penmanship. It's never been very good in the first place. And then if you put me with a plastic pen on a slippery screen, it looks like a third grader wrote your feedback. So if you can't read something, let me know. And also, the feedback is mostly meant to be for your benefit, to give you feedback. And I'm using a red pen, and if it looks like lots of angry writing, it's not. It's bad penmanship. It's just the nature of it. So I don't want you to think that I'm yelling at you. So anyway, just look at what I read, and then yeah, and if you have any questions, get a hold of me via email or come to office hours. So you will be able to see your feedback when I get things graded on written work. I only have the lab report from Chem Inquiry number 1 done. I don't have the safety thing or anything else for lab graded yet. Okay, so just a couple things about the first lab report that I wanted to note, and so I tried to make these notations as necessary on your feedback lab, and that is that, yep, significant figures, you got to get those rules down, the rules for addition and subtraction, which are different than the rules from multiplication and division. You have to know those. This is a quantitative course, which means we pay attention to our precision so we can be precise and accurate about the information that we're dealing with. There's other comments about recording and maintaining the precision of measured values. And so, in one of the calculations, you got a value of 0 for delta T and delta V. It's just not 0. It has to be 0.000. So get it in your head. Try to think about a measured value is not just a number. It's got a lot of hidden meaning inside of it. It's got the value. It has also, importantly, the level of precision. How well do you know that number? To how many decimal places? And whether it's 0 or any other number, you have to report that same number of decimal places. So, here are just some data. For example, you'll notice at the bottom that 0 down here, and this 0. 0 is not just 0, but a measured 0 is 0 to a certain level of precision, and that just has to be reflected. So the concept of significant figures is to always tell the reader how precise that measurement was, right? Do you see that? There's different levels of precision in these two columns. And you're telling the reader how well you know a number. That's the point of significant figures. It was not invented to drive chemistry students insane. It was actually invented to reflect in actually a pretty easy way once you learn it, our level of precision. So just one really quick thing. I copied an old whiteboard I had, but when you add and subtract, it's not about how many significant figures there are in the values that you're using. It's to which place is the uncertainty in the things that you're adding together. And, you know, this first one, these are volumes. They're all precise. And I always do it by circling the last significant figure so that when I take a sum or a difference, like I'm doing here, I always have to round to the leftmost decimal place in which there was an uncertainty. So in this difference between these two numbers, you'll notice that this figure there actually has 3 significant figures, and this figure here only has 2.099. And if you use the rule for multiplication and division, you would think you should round your answer to 2 significant figures, but that's not how it works. The rule is you're going to round to the decimal place where you have the most uncertainty, which essentially means the leftmost decimal place of all the numbers you're adding or subtracting, the one that's farthest to the left. And that happens to see that in that answer there, we still get 3 significant figures in that answer. And here's just an example where there were 2 of them. But I did want to note, this is a really common mistake. If you had something like this where you had to take the difference of these 2 and you do the subtraction on paper, I mean, you can do this in your head. 4.2 minus 2.2, you might be just satisfied to write a 2 down. That does not reflect the precision of the measurements. And you do need to write that 0 because remember our rule, circle the uncertainties. And then in the difference down here, your final answer gets rounded to the position, the decimal place, where there's the greatest uncertainty. In other words, the leftmost decimal place in any of these things we're adding or subtracting. And that happens to be right there. So just a few things just to keep working on. It's like I said last time, it's not going to go away. It'll be with you for the rest of your chemistry life. And once you get used to it, it's not so bad. Okay, enough of me yelling at you. So what are you going to turn in next week? It's all right here. The lab report from Chem Inquiry number 3, which you're doing today. You only need to turn in pages 86 through 95. Page 95, if you want to do it, is an extra credit. You don't have to do it. So technically it's really 86 through 94, but you can do the extra credit on page 95. And then there's a pre-lab for next week's lab on the wave nature of light. And I want to talk about that right now. And so basically it's another flow chart. We're getting you used to how to make these things and prepare for the lab. I want you to pay special attention. So actually, if you have your lab manual, if you have it, go to page 98 and you'll see this very instructions I have in front of me here. And I want you to take special notes so you don't do too much work. You're only going to do these specific sections that are notated right there. Part 1, steps 5 through 7, that'll be one flow chart. And then part 2, you're going to do the whole thing, which really isn't that long either. So you're going to make essentially 2 flow charts. And the next 2 pages in your lab manual are blank to allow you to create those flow charts there. This one is an example. And so actually in part 1, a lot of the work you're going to do is going to be similar to this. So you should sort of model your flow charts on the example given here. So that means then you're only going to turn in the 2 flow charts for which there are blank pages 99 and 100 in the lab manual. So this is what you're turning in. Okay? Need a minute to write that down? Okay, you can always come back to the video. So the report that you're going to write this week actually is doing a little bit of online research into nanotechnology, just going and looking at some links. There's a bunch of links in the lab report that you can spend all day typing into your browser, but if you go to D2L and look under the lab for week 3, I created a little PDF file that has all the links on there, and you can just open that on your computer. And if you actually click on the links on that PDF file, it'll take you to the web page. And that way you don't have to type in all of those links. So that's there for you to take, to use as you're going through the lab report for next week. So let's get into today's lab. So I just want to give you a little bit of background on nanotechnology, and that's going to lead us into talking about what we're doing, what you're going to watch today in lab. So this is just a little bit of background about that. If you read, it talked about stained glass as one of the first uses of nanotechnology. That was really kind of by accident. People, of course, in the the Middle Ages and in Roman times, as I'll tell you in a minute here, they didn't even have the concept of an atom. So they didn't really know what they were doing. They just had a way to do something that produced an interesting result. So for example, just some old pictures. On the picture is an old drawing of people in the early 1400s working at a glass factory. And they didn't know it, but they were nanotechnologists in the same way that the people over there on the right who are all wearing hooded things are working at the nanoparticle level, making nanotechnology or nanoparticle things. So yeah, they're both nanotechnologists. So what is nanotechnology? Just a little, I don't know if some of you have heard about it or I've never heard about it before. It's kind of the next biggest thing. I would be bad to not address this in a modern chemistry class. And so what is it? Well, it's the understanding and control of matter at really small sizes, roughly on the order of 1 to about 100 nanometers. And I'm going to walk you through just how tiny a nanometer is in a minute here. And the crazy thing is when you get down to particles that small, they have properties that actually people never would have predicted based on the way things behave at our scale, which we call the macro scale or even the micro scale. And so there's a lot to do. And one thing about nanotechnology is that, like, if you're thinking about what you want to do with your life, and maybe you like biology, maybe you like geology or chemistry or physics, and you just can't decide, nanotechnology is an area that draws on all of these fields or some of those fields as whatever you're interested in. It's just a really neat combination of lots of different science fields. So you can apply lots of interests that you might have, goes into human health and things like that as well, the environment. So, if you're really into this little tiny stuff, it's a great field to allow you to apply what you want to do into something you're really interested in. So a nanometer is like super small, right? Like if you remember the video from lecture today, a buckyball is 10 nanometers. In size. It's very small. And the thing is that we want to be able to harness materials at this level because they behave so interestingly and differently. So just to get you sort of a qualitative feeling for what a nanometer is, here are some scales, right? So you start out at the scale of a meter. People are about the scale of a meter, roughly. I mean, you're maybe a couple meters tall, but like a bicycle. So just here's what we're going to do. We're going to divide that size by 10. So imagine taking the length of an average bike and dividing it by 10. You get down to about the size of a cell phone, a modern smartphone. That's about a decimeter. And if you take that and just look at your phone and divide it into something 1/10 that size, you get to these little things like the size of a ladybug. It's a pretty big ladybug, a centimeter. That's a little bit less than 1/2 of an inch for us Americans. So that's still, you can still see that stuff, right? You can see a centimeter. It's marked off on a ruler. And now take that and divide that centimeter 10 more times. And if you have a ruler in front of you or something, you know, take a look at it. Those little centimeters divided up 10 more times and you get a millimeter. That's about the size of a grain of sand, roughly. All right, nothing shocking quite yet. These are all things that you can see with our eye. And for most of human history, this is how we thought of the world, right? We had no insight to anything that might be smaller than this. But somebody invented the microscope. And they looked at human blood and other fluids, it turns out, and they saw things that were 1,000 times smaller than a grain of sand. And so 1,000 times smaller than a millimeter, is where we were at with that sand, is a micrometer. And so this is the symbol for micro. And it's a Greek letter called mu. So if I go like this, I'm talking about a micrometer. And that is 1/1,000,000th or 10 to the -6th of a meter. So now you got to look at your ruler and take those little tiny millimeter marks and divide that into 1,000 smaller pieces. Pretty small, right? Well, that is still at what we call the micron, is another name for that. That's 1/1,000,000th of a meter. But we're not to the nanoscale yet. We got to go down another 1,000 times. You got to take that millimeter and divide it into 1,000,000 pieces to get to the micrometer size, or to get to the nanometer size, I should say. Well, before we get there, we have a scanning electron microscope at PCC here at Sylvania. Well, we're not there, but where I normally teach at the Sylvania campus. And you can see things down at the micron size. And a few years back, we had one of the raw ingredients you'll see used in lecture today is a solution of gold ions. And we had a big old jug of it sitting out. And over time, it reacted in the air and in the water, and it actually formed metallic gold. And these little gold atoms clustered together into particles. And eventually, because it had sat for a couple of years, they grew large enough to be able to see with the electron microscope that we have. And so I prepared a sample and I let some students take some pictures. So here are some pictures of little pieces of pure gold that had grown on the surface of this solution. I show you the size there, that little triangular piece. And you can see other triangular pieces. That is 20 microns wide. So that is, the length of that side is 1/1,000th of that millimeter, but it's still 1,000 times bigger than a nanoscale. But I just want you to look at that picture because it's cool. And the question is, why are they growing like triangles? When you think of metals, like why would they grow? They look like little prisms. Look at this guy from the edge right there. You are going to watch us grow. You won't be able to see them like this, but when you make the silver nanoparticles, when you watch us make the silver nanoparticles, you're going to grow little prisms that have that shape, except they're going to be 1,000 times smaller than this, too small to really see. But you might be asking, why does gold grow like a triangle? And you might remember back from the video I showed in the first week that said, what's the structure of a metal look like? And it was this sort of packing in there. This is a crystal of gold. But actually, if you could rotate this on to its edge and kind of look down from the point. So here are some pictures down here in the second row. And this shows how the atoms in a gold crystal are stacked. Every one of these little dots is a gold. And if you look at it from one perspective, it does look like a cube. But if you stare down from the corner, you can actually see there are planes of atoms that look like a triangle. You see me tracing this one out? And that's kind of an important thing, especially relative to today's lab. It actually turns out that the atoms are closer together along the edges of this triangle. I don't know if you can see that along an edge. than they would be along the sides, the edges of a cube. So you can find these little triangles in all sorts of different orientations. And it's the fact that those are what we call the closest packed atoms. They're packed in more closely along these sort of dimensions of that cube, you know, these diagonals. When metals tend to grow, they tend to grow along those orientations. And they grow, they just keep growing out along the edges of those close packed planes. And so you get these little prisms that look like this. So it takes a long time to recognize it as a cube, but it will eventually sort of look like that at some point. But they start out as little nanoprisms, they're called. This little background for you. Here's somebody else took a photograph. You can see the little pieces of gold. You can see it looks like a metal, right? It's all malleable. The little guys are sort of bent over. That's a property of metals, right? If we were growing crystals of sodium chloride, you would not see all this folding and warping as we go along here. It's certainly a metallic thing. The other crap that you see in the background are just smaller pieces of gold that are still too small for us to see with in this sort of detail with the electron microscope that we had. So anyway, but again, the nanoscale is 1,000 times smaller than this. Those were just microparticles. So if we go down 1,000 times, this is the level of stuff that we're at. It's, you know, take a red blood cell or something at the micrometer scale. Now we're at a billionth. 10 to the minus 9 is what nano means. Nanoscale. 10 to the minus 9. Well, these are some things that exist, this detail at the nanoscale. Viruses, you're all familiar with viruses now. They're that small, that's why they're so problematic. They're much smaller than bacteria. There are atoms and buckyballs and nanotubes and DNA. That's a really small scale. Just imagine in this lab today, we're going to get through chemistry a chance to manipulate things at that scale. If you had taken chemistry lab 25 years ago, this would have been unheard of. So one of the first things that was used for this was stained glass. I will imagine that most of you, if not all of you, have seen an example of stained glass windows. Either just in regular art, or if you've looked at pictures of them or seen them in some sort of building where they have stained glass. They're just really beautiful. How do you make glass? Well, glass, you just take sand and melt it. You add a couple extra ingredients. These two right here, you know, if you imagine trying to melt sand, it would melt at a really high temperature. And amazingly, if you add these other chemicals, it lowers the melting point of sand. And so it gets to the point where medieval individuals and ancient Romans could actually get that sand to melt and turn into glass, just basically quartz. And here's where the nanotechnology comes in. You can add other chemicals to create color. Typically, they would just go and find rocks in the ground, like they would, excuse me, they would add things to make them red. They might find iron or other element containing minerals and add that to the molten glass, and that would give you color. But here's an example of a stained glass window from a French cathedral. And if you look, there's a lot of yellow and red in there. And you might be asking yourself, well, what element, you know, could I add? What stuff could I add to make those colors? And it actually turns out the yellow comes from adding silver in nanoparticle form, and the red comes from gold, which you wouldn't think of, because when you think of gold, you don't think of red. And when you think of silver, you don't think of yellow. But I just want to show you something really kind of cool. The ancient Romans, this is around the 4th century, so 300 and something AD, crafted this cup that they made out of glass. This central part of this cup, that's all glass that they carved away to make these figures. Excuse me for a second. Okay, I'm back. Anyway, They knew that if they added finely ground gold and silver into molten glass and cooled it and formed it, they would get this thing. But the weird thing about this cup is that light that is reflected off of it looks different than light that is transmitted through it. And I just got a really quick 1 minute video here, if I can get this to work, to show you that, maybe. Nothing works. Ignore the music. So here you're kind of looking at light. It looks green. It's in the museum. So they're going to show you what happens when the external light, and now that's light that's shining down that's being transmitted through the cup, and it looks red. And you can imagine that, well, it's still pretty amazing to me, but imagine how kind of magical this must have seemed to ancient people to be able to have something that changed color depending on how you looked at it. That is just really amazing. And that's just something that is a result of there being nanoparticles of gold and silver in there. Just a really neat thing. So they were doing nanotechnology back in the old days. They weren't exactly sure what was going on, but they were doing it. So the thing to take away from all this discussion is the size of the particle really does make a difference in terms of its properties. And so gold and silver look like that in what we call the bulk phase, but at the nanoscale, they have completely different and unpredictable colors. And you will see examples of us creating particles to give us these sorts of colors. It's really very interesting. So at the nanoscale, if we can change properties like the size of the particles, that will give us different colors. So the images that you're seeing here are from an electron microscope, which doesn't give us color like a photograph. But I'll show you in a minute, the thing that looks colored are the solutions that you get, the solutions that you get when you create particles of that size. And so it actually turns out that if you make gold particles of these different sizes, you will see mixtures that have different color to them. And so at some point in our life, we would want to be able to explain why. Why does that happen? Why does making a gold particle go from 25 to 100 nanometers in size change in color from red to orange? And so I hope that you're thinking, how the heck does light interact with matter? You know, are the gold particles themselves, are they red or green or orange? Do the particles have like they were painted? Or is it something else? I'll give you a hint. They're not colored themselves. It's how they affect the light that passes through them. And that is a subject for next week. But it's pretty cool to see. Not only if you change the size, do you get different colored mixtures, but if you change the shape. So this one shows that if you had silver this time at 40 nanometers, you'll get a mixture that looks blue. But if you let them grow bigger up to 100, it would look yellow. And this is kind of what they were getting in the stained glass. They just really were uncontrolled growth of these little particles, and they got big enough and it just looked yellow when it was dissolved in the molten glass. But the crazy thing is, if they could have changed the shape of the particles and made these little triangular prisms, then it would have looked red. So the size and the shape are ways that we can control things at the nanoscale to affect the properties that they have. The goal is influence what happens at the nanoscale so we can get properties of things that we want. Just a little interesting background, kind of related to what we're going to do today. We're going to make little nanoprisms, but we're going to change the size, and that's going to give us different colors. Just what are some related things that are useful? Why would we care to make nanoparticles? Nanoparticles are huge in medical research right now. Everybody is looking for a cure for cancer. And if you know anything about chemotherapy, what you do is you take a toxic chemical that essentially can't discriminate between healthy cells and cancer cells. And so usually they target the cells that are the fastest reproducing. And so that's why people who are on chemotherapy often have lots of gastrointestinal issues, and you lose your hair. These are cells in the body that reproduce and replenish themselves very rapidly. So the chemicals in chemotherapy that they're given attack all of those kinds of cells, including the cancer, which is also reproducing. You know, they're cells that just reproduce out of control and form tumors. It's not a pleasant thing. So hopefully the idea is that you kill the cancer before you kill the patient. Now, imagine if you could design a delivery method that, when given to a patient, only attacked the cancer cells. And what we're thinking of doing is to take a nanoparticle. For example, this is a bit of an old research. This is back in 2003. But one way to do that is they took tiny little glass beads, only a few nanometers across, and you encased it in gold. And so you made like a little walnut shell of gold on the outside. And then there are these little guys sticking out of the top here. And what those do is those are ways that this particle can find particular types of cells. And so if you ever had biology class, maybe you know you got a little cell over here. On the surface of the cell, there's all sorts of little proteins and sugar molecules sticking out that have different shapes on them. And this is kind of a way that cells communicate with the outside world. And so what you do is, when cancer cells grow, sometimes they have unique little protuberances, little flags sticking out here that healthy cells do not have. And so if you build your little nanoparticle and stick on a complementary shaped little flag, then when you ingest it, it'll link up with the cancer cell, but it will leave regular healthy cells behind. And so what you do is you give your patient the little beads here, the gold-coated nanoparticles or other similar things. And if you remember from lecture today, they talked about buckyball carrying drugs. That's what they did to try and use buckyballs. They put these little sort of signaling flags out here, and so that it would attach to different types of cells. Different types of cells in your body have different little flags sticking out of them. And so we can target them. That's called targeted medicine. And that's the dream of the future. So anyway, you inject a patient, give them some of these gold nano shells. It works its way through the body, just bypasses all the healthy cells. But when it runs into a cancer cell, it's going to stick right onto there. So there's my little bead. And when it gets there, in this particular issue, or this particular case, what they did was you could then put infrared radiation around the cancer area, and that causes the metal to heat up. And it heats up enough, you only need to get it up to increasing the temperature by an extra 54 degrees Fahrenheit will kill those cancer cells. But because there's no gold particles on the healthy cells, they're not affected. And I can't remember the reason why this technique didn't exactly work, but it's kind of an idea. That's how nanoparticles are involved in targeted medicine, and it's a hot area of research. There's silver, can be used as well. Silver's already being used. You can buy silver nanoparticle clothing that you can get, things that are impregnated with silver nanoparticles. And the reason is because little silver nanoparticles, what you want to do to prevent spoilage and stinky armpits in your clothing is to prevent bacteria from growing. That's what causes food to spoil and your body to stink in certain locations. So the silver actually has the effect of being able to get in and destroy the bacterial cell. But you, a big giant person, doesn't really harm you. So that's already out there. Nanotechnology, silver nanoparticles, that's out there. And, you can just look this up on the internet. Now, people do all sorts of crazy things in life. And so some people believed, I'm kidding you not, that's a real picture. He's not wearing makeup. A lot of people believe that if you take silver nanoparticles in significant quantities and drink it every day, it has some sort of life-preserving effect. And so this guy, they used to call him the Smurf Man from the cartoon Smurfs, which were blue. Anyway, silver, when exposed to light, tends to turn black. And so this guy is normally kind of a pinkish-skinned individual. But so much of that silver lodged in his skin that the black from the silver particles and the pink from his skin turned him kind of this weird looking blackish blue. That was his natural color, believe it or not. And he died not too long after this picture. I don't remember what he died from, but a lot of people are into this. It's kind of bullshit. We like to call it pseudoscience, not real science. And I just wanted to, this gives me an opportunity to have you think about all the pseudoscience that's out there. And I just randomly did a search on the internet for colloidal silver. And this is one of the things that I came up with. So people are selling the same sort of solution that that guy drank that you can take for your pets. And one thing you should be aware of when you look on the internet and somebody's trying to tell you something, turn on what I like to call your bullshit detector. And that is to look at what they're claiming in the ad and seeing if there's any real evidence behind these claims. And so I just want to show you a couple things to get you thinking about this, because you just see this stuff. I promise you, walk down to Whole Foods or the other stores, you will just find this stuff on the shelves all over the place. And a lot of it is, excuse my language, but it's bullshit. Let's see what this is supposed to do. Here are things that you can look out for. Avoid expensive veterinary bills, and there is no cure-all. One thing to think about when you're thinking about whether something works or not is if it really worked, it would be out there on the market and people would be making lots of money from it. If you think it's all a conspiracy that Big Pharma is withholding important drugs from us, believe me, if colloidal silver was a cure-all, they would invest in that and sell it to you and make a lot of money. It's ridiculous to think that, to think otherwise. But I just want to show you some other claims. Again, now it's an all-around good cure, right? So like I showed you earlier, silver nanoparticles do have some effectiveness against, in certain situations, bacteria. But there's no evidence that it has all these different things that this is claiming to cure in an organism like an animal or a human. Well, we're animals. But it says helps repair tissue damage and soothes the skin. There is no evidence for this. They are just making claims. There's no scientific evidence that says that colloidal silver, which this is called, has any tissue repair effect. An immune booster, zero evidence for that to be true. People are making these claims. My favorite part about this whole ad was they make all these claims and then they go down here and they say, we're not licensed health professionals and we do not claim that silver can treat any of the diseases of any kind. I mean, they're making claims and then they're telling you they're not making any claims. Yeah, you should just click on through. Is it super effective or is it a cure-all? Well, here it's possibly effective. It can possibly help. Anyway, just be wary when you look at some of these things that are out there. A lot of people like to take modern innovations in science and use the buzzwords and sell you a bunch of crap because it sounds sciencey. So you just have to be aware that there's a lot of that garbage out there. Okay, enough of my going on and on. I'm gonna let you get started. I have a couple announcements about this lab that you're gonna wanna pay attention to if you've been sleeping up till now. And so here we go. We are not gonna do part one. We used to be able to get a mixture of buckyballs, C60 and C70, and we used to do this thing where we looked at separating those two and all this sort of fun stuff. We're not going to do that because the source that we had for that has not had them recently. So we're not going to do part one. Part one. not doing, which means you are not going to do part 1 on page 85 of the lab report. Good news. The background reading, you are going to do parts 2, 3, and 4. Starts on 76. That's what you're going to work with today. The video that you're going to watch is going to start here on page 78 in the manual. So you should watch these steps as you move along. And watching that, the first one we're going to make gold nanoparticles. You don't have to go to this optional video here. It's just it's just somebody else doing that in more broken down steps. But regardless, watch the video that I've got posted on D2L. This will be the first place. We are going to go all the way through to the end. The last part finishes with part 4, investigating, do we really have nanoparticles or not? How do we know that? So we're going to start thinking about how matter interacts with light is kind of a theme for today as well. So, yep, stick it out till the bitter end. And I think I already showed this slide, but background reading starts on page 76. Here's kind of what you're missing out on. These are vials of nanoparticles of different sizes we did one year. They're beautiful. We tried to do some artistic photography in the lab, so you'll see how that goes. And so the thing about this is that these are vials. This is not like Kool-Aid. These are vials of metal particles suspended in water, and different sized particles give you different colors to the mixtures. And so that was part of the goal for today. And before I let you go, I discussed this in the lab, but I kind of talked through it, and I just want to talk about, in a way, I hope that you'll be able to understand what the hell is going on today. And so here is how you start with an ion of silver. And at the end of the day, you get a prism of silver metal. And so I'll just go through this briefly. It's not incredibly, you're not going to be tested on this process, but it's good to know just what it is you're watching to give you a little bit of background. So this will take me about 5 more minutes, and then you'll be able to go ahead and get started. So here's the deal. Presumably you've read through the pre-lab, and what we're going to have here at the start are silver ions. So we're actually going to take a solution of silver nitrate. That is one of the first things that gets added. And so this is silver nitrate as a solid, looks like table salt. And you dissolve it in water and you get a solution of silver nitrate. So when you put it into water, what you get are sort of free floating silver ions, and you get some nitrate ions. We don't care about the nitrate. What we're interested in are silver ions. Now this is an ion, remember. Our objective is to get a silver metal. In other words, silver that doesn't have a charge. Well, what is a silver ion missing compared to silver metal? Well, we need some electrons, right? Every silver ion that's floating in solution needs some electrons. There's lots of ways you can do this. If you take Chem 223, we can stick electrodes in the solution and pump in electrons that way. But we're going to use a chemical tool. And this is the chemical tool called a reducing agent. And it's another chemical. It's got this formula. And this is sodium borohydride. That's the name of that. And without going into the details, sodium borohydride, when you dissolve it in water, is what we call an electron donor. So if you take some sodium borohydride and mix it with silver ions, sodium borohydride donates electrons to silver plus, and it's going to form silver. I put a little 0 there, metallic silver. And what's going to happen to the sodium borohydride once it gives off electrons? Who cares? Just going to make stuff you don't care about. We're focusing on one of the products, silver. Well, if you let this continue to happen, the little silver atoms are going to start to pile on together and grow little tiny metal crystals like I showed you in those electron microscope pictures earlier today. Well, if you think about it, what's the problem? Do you think that metal floats in water? No, we all know that metal is going to sink in water. So if I want my little growing particles of silver metal to stay suspended in water, that is something that's called a colloid. So this is, if I can get this all on here, particles suspended. And most commonly, it doesn't have to be water, but we're just for today going to say water. Like milk is a colloid. So we're so used to homogenized milk if you buy it at the store, but if you get fresh milk from an animal and let it sit, it separates out. You get kind of a watery layer, and then you get a layer of cream, which is fat and protein, and then you get another layer. So colloids tend to, well, they can separate out over time, and the goal is to kind of make it stable. That's what homogenization of milk does, but that's another lecture. So what we have to do is stabilize the silver particles so that they stay suspended so that we can look at their beautiful colors. So what we have to do is we have to put a coating on. And the coating that we're going to add is something called citrate. Now, what is citrate? Well, citrate is a form of citric acid. Ever heard of citric acid? From citrus fruits. That is the tart or sour acid that is common in most fruits. You can convert that into an ionic compound called sodium citrate. And it turns out that the sodium citrate, what you do is you cause citric acid to become a negative ion. So citrate, the name has changed. It's a negative ion. And so it turns out that ionic things love to dissolve in water. So what we're going to do is take sodium citrate. We don't care about the sodium anymore. It's the citrate that we're after, this guy with a negative charge. And we're going to coat it onto the surface of our growing little nanoparticle of silver. And they kind of stick out like little hairs growing out of the silver particle. One end of the citrate molecule is attracted to the metallic silver, and the negatively charged end of the citrate molecule likes to dissolve in water. So what have we done? We've taken our metal particle that wanted to fall down to the ground, to the bottom of the container, and we've given it essentially a hairy, charged coating. And now this particle looks like it's got a bunch of charges on its outer skin, and now it will dissolve in water. So we have actually, by putting this sodium citrate on, we've made silver particles that are soluble or can dissolve in water. So now we've solved the suspension problem. We've got our silver particles growing randomly. But remember, the goal was to make not just a blob like that. We wanted to make this thing. And that's the interesting thing. The question is, how do you control so that the little silver blob grows into the shape of a little prism? Well, you add our next chemical ingredient, and that is a thing that's called an etchant. And an etchant does just what it says. It's going to etch this particle from a blob. Let's see if I can erase this. It's going to take our misshapen formed blob, and just imagine, you had a file. You just filed it off here, and you filed off this garbage, and you filed off that garbage until it was in the shape of a prism. And that etchant that we're going to use is hydrogen peroxide. That's the formula for, it's the same hydrogen peroxide that you can buy at the grocery store that you can use in your home. Actually, even more dilute than what you have. And actually, the way the etchant works is, if you remember a few slides back when I showed you the structure of that the gold little triangular particle that grew, The etchant tends to work along those planes in the crystal where the atoms are most closely packed together. And if you just sort of randomly etch along those planes, you end up with a prism. That's a super oversimplification, but that's how it works. Okay, so let's just review. What have we accomplished? We took silver ions and we added electrons by adding sodium borohydride, and then we made silver particles, and we're going to let them grow. But if they grow too big, they're going to fall to the bottom of the beaker, and who cares? So we have to make them float. These are like little life preservers. They're little charged molecules that stick on and give our silver particles hairy protuberances with charges on them, and that allows them to float because things with charges tend to be able to dissolve in water. And once they're able to float, we have to carve them into the perfect shape. And that is by adding hydrogen peroxide. That's going to etch them into little triangles. But we're not done yet. Remember, now that we've got them into prism shaped, we got to control how big they get. So I have this other slide, and just let me walk you through this. The way we do that is with the last thing that we add, and that is what's called a capping agent. Capping agent. That means put a cap on it. Coat the surface at some point so that no more silver atoms can join the party. We're going to restrict the growth. And the way we do that is by adding another chemical. The other chemical that we're going to add is potassium bromide, KBr. It's an ionic compound. When it dissolves in water, forms potassium ions and bromide ions. Who cares about the potassium? It's the bromide we're interested in. Because the deal is, silver ions in the solution and bromide ions really, really love each other. And when they get into contact with each other, they make this new compound, ionic compound called silver bromide that does not dissolve. That's an E. Some ionic compounds, potassium bromide, easily dissolves in water and breaks apart into ions. Other ionic combinations do not dissolve in water. In fact, if silver ions and bromide ions get together, there's such an affinity for each other that they will, we say, precipitate out of solution. They'll form a solid, and they are actually going to form it on the surface of these prisms. So think about what we could do. If we add a lot of bromide to the solution, it'll very quickly form silver bromide on the surface of my little nanoprism, and that will cap it. That'll prevent any further growth. And that's going to make lots of small nanoprisms. So lots of silver, lots of potassium bromide added makes small nanoprisms. If you don't add any potassium bromide or just a small amount, then it's going to take a long time until the coating forms and the particles grow very big. So small amount of capping agent gives you big particles. Large amount of capping agent stops the growth, gives you small particles. So that's the whole thing in an overview. And the weird thing is we actually add all of the other ingredients first. And at the very end, you'll see we add the reducing agent because we want to make sure we have all the other things in there and ready to go, including this, before we add the reducing agent that starts the whole process. So sodium borohydride is the last thing we're going to add after we've prepared these mixtures. And so things to think about, you can ignore that, is that the size of the prism determines which wavelength of light gets absorbed. And it actually turns out that if your prisms are small, how do you make small prisms? You add a lot of capping agent. They are going to absorb short wavelength blue light. Is that going to make them look blue? Good question. If you don't add any or very small amounts of capping agent, we're going to get big prisms. And big prisms absorb red light. What's that going to look like? Good question. All right, I'm finally done talking. You can go ahead and get started with the lab.